Hello and welcome. In this session, we will try to learn the shear force and bending moment diagram for an overhanged beam. So first, let's understand that what is an overhanged beam. It is basically combination of your cantilever beam as well as your simply supported beam. So here I am showing two types of overhanged beam. One is known as the single side overhang. So here you can identify that this is an overhanged portion and remaining is considered as a simply supported portion. So this type of beam where one side is just overhanged called the single side overhanged beam. On the other hand, this is double sided overhanged beam. So we will try to learn that how we can make shear force and bending moment diagram, because this is the most commonly asked problem in the examinations, as well as it requires more thinking and more detailed analysis to make the shear force and bending moment diagram. So let's start with one example. That here I am showing a beam where, if you will see, this is a pin joint, this is a roller joint, this is a overhanged part, and the length is 1 meter, 2 meter and 2 meter. These two are the uniformly distributed load. 50 kilonewton per meter is the intensity of this load. 20 kilonewton per meter is the strength of this. There is another point load acting at this point of magnitude 30 kilonewton. So now we have to make the shear force and bending moment diagram for this beam. So we know that before getting the reactions, it is not possible to make the shear force and bending moment diagram for overhanged beam as well as for the simply supported beam. So first job is to calculate the reactions. Now how we can calculate the reactions? So to calculate the reactions, we have to first consider an equivalent beam. So now here I am representing the equivalent beam, and what I did here, instead of having the uniformly distributed load, I have converted these two loads into point load. And how I did that? This is 50 kilonewton load acting for a span of 2 meters. So if I will remove this and I will assume a point load, that would become 50 into 2, and it will act at a distance 1 meter from this end, because the total distance is 2. So it will act from the centroid of this length, so it will be at 1 meter. Now 30 will be as it is. Similarly, this is acting at a 1 meter length, so 20 into 1, and that will act at a distance 0.5 from point C. Now we have to apply the law of statics to get the reactions RA and RC. First I will apply the force balance. In case of force balance, total vertical downward load will balance by total vertically upward load. So these are RA plus RC. The total downward load is 100 plus 30 plus 20, so it would be 150 kilonewton. The second equation I can get by taking the moment at any point. Normally what I do, I calculate the moment at the extreme point, not at the midpoint, because when you are taking the moment at this point, you have to take care of the sign, because 20 will have a clockwise movement, but 30 and the 50 into 2 will have the counterclockwise movement. So to avoid this confusion, let's take the moment at point A. So when I will write the moment equation at point A, this will be 100 into 1, and the sense will be clockwise. This is 30 into 2, that is also clockwise. Then 20 into this total distance, which is 4.5. So 3 moments, because of the 3 vertically downward force, will be 100 into 1, 30 into 2 and 20 into 4.5. Then your RC into 4. So this is your RC into 4. When I am solving this, I am getting that my RC is coming out 62.5 and RA is coming out 87.5 kilonewton. As now I have calculated two reactions, so let's start that. Now this is my beam where these are the two known reaction to me, and now I have to make the shear force and bending moment diagram. So let's start with the shear force diagram. So this is the representation of your beam, and I will start from the extreme right point, and so I will move from right to left side. So first let's make this is A, B, C and D points, and first I will make the shear force diagram for section D to C. For doing that, as I know that this is a uniformly distributed load, so what I will do, I will assume a distance x between C and D. So this is point C and this is point D. I am assuming somewhere in between a point x. And why I am doing so? Because whatever equation I will calculate for this point, that would be valid for point up to point C. So my shear force at point X will be what? I know that as I will move from this right to left, whatever force will come in my path will be subjected as a shear force. So for this length, the force will be X into the intensity of this loading, that is 20. So my shear force at point X will be 20 into X. Now this equation is valid till point C. So if I will put X is equal to 1 meter, because this is 1 meter, I will get the shear force at point C will be 20 kilonewton. This 20 kilonewton calculated using the equation developed for the section C and D. And what is the direction? So I already explained this in my previous classes that for the downward loading I am assuming my shear force will be negative. So this is your downward load. So for downward loading my shear force will be negative. So I will make a shear force diagram here. This would be a straight line, and I know here that it is a function of X. That means as my X will increase, the shear force magnitude will increase. So at this point my shear force will become 20, and that is on the negative side. Now I will start writing the shear force for between point C to B. So before I write for C to B, there is another force acting at point C. So first I will take care of this loading, and how I can do that? I know that now using this part, I know I have calculated that my shear force will be minus 20. So now I am having a sudden point load that is of magnitude 62.5 and acting in the upward direction. So that is a positive 62.5. So my net force at point C will become plus 62.5 minus 20. That will comes out at 42.5, and that is positive. That means at the point C, when I am moving from this side to this side, I am experiencing a negative shear force, but suddenly this point comes, so I will experience a positive. So my line will go toward the positive side, and this height from here to here, it is 42.5, because this is your absolute value. Now beyond that, when I will write the equation for C to B, I can see here that there is no any other force in this gap. So whatever shear force I have calculated at this point will remain constant till point B. So shear force between C to B will have same value 42.5, that is valid till point B. So my shear force diagram will constant till point B. So now this is the negative part, this is the positive part of my shear force. As I will reach at point B, now I know that there is a sudden a point load of 30 kilonewton, and that is acting in the downward direction. So at point B, my previous shear force is 42.5, and suddenly there is a 30 kilonewton force in the downward direction, so it will be negative. So finally I will be having 12.5 kilonewton shear force at point B. So my line will go in the downward direction, it will reach somewhere here, because I know this is 42.5, so this is 30 down, that means this small value will be 12.5. Now after that, again a uniformly distributed load. So whenever we have uniformly distributed load, we cannot directly make the shear force diagram, we have to consider a distance of X. So here I am showing that now I am at this region which is AB. I am considering a distance X. If you will see different books, you will find sometime the X distance is measured from this point, sometime it is measured from this point, but normally what I do, I assume my X every time from the extreme right position. So here this is my X position, and till this point, if I am interested to write the shear force, what will be my shear force? There are two ways. One, you can just consider the shear force at this point and include this portion, or you can start from the extreme right. So if I will start from the extreme right, 20 is a negative sign. You see, instead of having a uniformly distributed load, as I have now cross this uniformly distributed load region, I can consider this UDL as a point load. So now my point load will be 20, and why it is 20? Because it is the span of this 20 kilonewton per meter intensity load is 1 meter. So net load will be 1 into 20, that will be 20. So 20 negative, 62.5 positive, then 30 negative, and remaining this load which is of UDL load. So that will be what? that will be the intensity of this load multiplied by this distance, and this distance will be x minus this distance. This is 1, this is 2, so it will be x minus 3, and intensity of this load is 50 given here, so it will be 50. It is acting in the downward direction, so it is minus 50 x minus 3. This is equation for the shear force that will be valid till point A. So now if I will put x is equal to 5 here, because if I am interested to find the shear force at this point, so I am going to put my x will be total length, that is 1 plus 2 plus 2, that is 5. If I will put a for a x is equal to 5, when I will put 5 in this equation, I am getting a value minus 87.5. And you should remember, as you have already calculated a reaction that is 87.5, so this is your cross check, that when you will start from this value, this position, when you will reach to this position, your force, shear force should be equal to the reaction, and then when this minus 87.5 will come, and then again the 87.5 plus will come here, the finally you will get a 0 shear force value. So your diagram will look like that you are having a value 87.5 minus, so currently you are 12.5 in the plus direction, so you will go somewhere here, that will be the minus 87.5, and ultimately you will reach back to this position. Now you can see here that you have crossed the zero line. That means your shear force has changed its sign from positive to negative. So sometimes it is also asked that what is the position of this point where your shear force is changing its sign. So you have to calculate this x value, which you can calculate by putting 0 in this equation. So if I will put shear force 0 here, my equation will be minus 50 plus 62.5, then minus 50 x minus 3. When I will solve this equation, I will get an x value that will represent the position where shear force is changing its sign. Now quickly see the bending moment. So now for making the bending moment, this is the again I'm assuming this is my beam, and I will start for bending moment of region C to D. So when I will start my bending moment for a zone that is C to D, again as I have calculated previously for the shear force, I am assuming a point x here, and for this x length I am writing the equation for the bending moment, and this equation will valid till point C, from D to C. So you know this is your uniformly distributed load, and we have seen that the uniformly distributed load will first convert in the point load that will be of magnitude 20 into x, and the force will act at the center of this length. This is the length x, so my force will be assumed to act at point x by 2 from this x point. Now if I am interested to find the moment at this point, my moment will be what, 20x into x by 2. So this is 20x square by 2. Normally you will find in the book that the intensity of the bending moment for the uniform distributed load is given as wx square by 2. So either you can remember this formula and directly apply, or you can just consider that for this length, if I am writing the bending moment for this length, the length carries a uniformly distributed load of magnitude 20 Newton per meter. So first I will convert it into a point load. This is my point load, and the point load is acting at the center of this length. So it will be at 20x, 20x load is acting at x by 2 distance, and I am taking moment at this point. So this is my equation for the bending moment. This equation is valid till point C. So if I will calculate the bending moment at point C, I will put x is equal to 1, because this is the total length is 1. When I will put x is equal to 1, my bending moment is coming out 10 kilonewton meter. But the sense of the bending moment, as force is acting in the downward direction, and I am interested to find the moment at this point, so it will be having a clockwise sense, so it will be negative. Now if I will see the equation, this is not a linear equation, but when we have seen the equation for the shear force diagram, we observed that the equation is a function of x only, but here it is a function of x square. That means the variation will be of parabolic nature, not the linear nature. And I know now that the bending moment at this point will be of magnitude minus 10. but it is of negative sign. That means the shear force at this point will be minus 10, but the question arises that it will be having a parabolic nature. So there are two types of parabola. One parabola would like this way, in this way, another parabola can be in this way, and both will have a value of minus 10 here, minus 10 here. So which is correct which is the correct solution? So now to understand that whether this one is okay or this one is okay, you have to go back and you have to check the value of shear force. Why? Because the slope of the bending moment diagram represent the shear force value. Please remember this, that del bending moment divided by x will represent the shear force. So in my case, if I will see the shear force value at this extreme point, here is the shear force value and I can see this is 0. That means for point D, the shear force is having a value 0. So my bending moment curve should have a 0 slope for point D. If now I will compare these two curves, one curve which is having a pattern like this, so we can assume that the slope at this point will be 0. Slope means the angle of the curve with respect to this horizontal line. On the other end, if I will see this parabola is going in this way, that means there is no 0 angle, it is having some angle. So this is a non-zero slope at point D. So we know that shear force is 0 at point D. That means this is the correct parabola. A shortcut is there that whenever you are making the bending moment below the line, it will be a concave shape. When you are making the parabola above the line, it will be a parabolic shape. So now I have find that my bending moment for from point D to C will be a parabola, and it will be like that, and value at this point will be minus 10. Now after point C, again I will write equation for the bending moment between the section B and C. So for that, this is my beam now, and now I am writing equation bending moment for this section. So as I have already crossed the uniformly distributed load, now I can assume this uniformly distributed load as a point load. So I have replaced this UDL with a point load of magnitude 20 into the length, that is 1, so it will be 20 kilonewton. This is my point of C where I am having an upward reaction, and I am writing equation for this line. So again I am assuming a distance x from the extreme right point D, and I am writing equation for bending moment at this section. So this section, it will be having 20 into this length. This length is x minus 0.5 and 62.5 into this distance. So that would be 62.5 into x minus 1. So my bending moment equation will be minus 20. Why I am putting minus? Because I know that clockwise bending moment should be negative and counterclockwise would be positive. So this 20 is having a sense clockwise here. On the other end, 62.5 is having a sense of counterclockwise. So this is plus 62.5, this is minus 20, and distance is x minus 0.5. Here distance is x minus 1. Now this equation is valid till point B. So when I will put my x is equal to 1 plus 2, so at point B x will be 3. When I will put 3 here, I am getting my bending moment is coming out 75, and my expression is a function of x only, it is not a function of x square. That means it is a linear variation. So now from minus 10 I have to go to a value of plus 75, and that will be a straight line. So here the bending moment will have some value plus 75, and that will be a straight line, and this length will be plus 75. So here also you can see that the bending moment diagram is changing its sign. It is moving from negative zone to positive zone. So here also it is important to find this x value, which will represent a point where your bending moment diagram is changing your sign. And how you can get it? If you will put this bending moment 0, you will get x value, and that will represent this point. So when I will put this bending moment 0, I will get x value that is coming out 1.23 meter. That 1.23 meter is this distance, and this point where the bending moment is changing sign known as the point of contraflexure. Please remember this point, because it is sometime asked in your gate examination that what is the point of contraflexure. The point of contraflexure is a point where bending moment changes its sign. After reaching to point B, now I am interested to write the bending moment for the zone AB. So again what I will do, I will write the equation for bending moment at this point, and for that what I will do, now I will assume my x distance up to this point. this is my x distance, and now I will write equation for your bending moment, and that would be what? That equation will be bending moment because of this loading. So I will make an equivalent diagram here. This is the 62.5, this is 20, this is 30, and I am writing equation for this length. So this is UDL, and that UDL will considered as a point load of magnitude 50 into x. So this is 50 into x and acting at a distance which is what? So half of this distance. And what is this distance? So this total distance is x minus 3. So this distance will be what? X minus 3 by 2. Now I will write the moment equation. So I will write that the 20 and to this distance, this is what? Total distance is x minus 0.5. So 20 into x minus 5. If you will recall our previous equation, there is add-on of a new term on the previous equation, but here again I am writing the equation from the scrap. Otherwise, what you can do, if you will see our previous equation, in the previous equation is minus 20x minus 0.5, then 62.5. so I will get these two terms, and then I will add another term because of these two forces. So this will be minus 20x minus 0.5, it is 0.5. Then I am having a force of 62.5, that will be having a counterclockwise sense. So I will write plus 62.5 into this. This is what? X minus 1. So I am writing it x minus 1. Now third force is 30 Newton. That is acting in the downward direction. So it is having a sense of clockwise. So I am writing this 30. And this distance is x minus 3. So it is x minus 3. And now fourth one is the uniformly distributed load. So I know that the magnitude of my force is 50x. It is acting in the downward direction. So it will be minus 50x. And the distance is x minus 3 by 2. So it will be x minus 3 by 2. And that is the bending moment for this point. And this equation is valid till your point A. So this is the bending moment for x distance. And this is valid for point A. So when I will write that x is equal to 1 plus 2 plus 2, 5. When I will put this value in this equation, this is the combination. These are the linear term, but this is a parabolic term. That means your bending moment variation will not be linear. It will be of parabolic nature. And finally, you know that this is a pin joint. This is a trick. Actually, you no need to calculate now this value. You know that when you will reach here, your bending moment should be 0 because this is a pin joint. So what you can do, you can simply make a parabolic curve which is going to be end at this point. Now again the question arises that this parabola or this parabola. So please remember that every time you have to check that what will be the slope of the parabola. So when I will see at this point my shear force is minus 87.5, that means it is not a 0 value. Ultimately it is reaching to the 0 value, but first it is having some value and then 0. That means slope should not be 0 here, and my bending moment curve will look like this way. So this is the bending moment curve and this is the shear force curve. I know that this question is little bit lengthy and you have to practice it, then only you can solve it in the examination. But I tried my best to explain you the complete philosophy. Now you have to practice so that you can complete this problem in 20 minutes in the examination. Or when you will see such types of problem in your other competitive exams, there you will not ask the complete question, you may be asked few part of your question, so you should be thorough about it, then only you will be able to attempt those problems. Thank you. Now in my next video I will try to explain the double side overhanged beam, but normally if you will understand the single side overhang condition, you can extend it to the double side overhang condition. Thank you.